Okay, welcome to this session. My name is Guillaume Lavallée. I'm Product Line Manager at Expo. I'm joined here today with Chris Todd, Program Manager at Senko Advanced Component, as well as Annabelle Alarcon from Expo. She is a product specialist with us. So today we want to do this session to talk about the speed migration to data center, optics, and breakout with Senko. So Senko, they introduced some very small form factor optical connectors, such as the duplex CS, the duplex SM. And Chris is with us today to present us those new connectors, their characteristics, their advantages. After this, myself, I'm in charge of the fiber inspection scopes at Expo. So I'm going to show you how to inspect such a connector, how to clean such a connector, and make sure everything is okay. So I'm going to switch camera and do a live demo on how to do that. After this, my colleague Annabelle is going to also do a demo, and she's going to concentrate on the protocol testing, show you how to test those breakout cable connection that are using the CS connector that you can find in an environment such as data center or maybe in central offices. So without further introduction, I'm going to ask Chris, who's with Senko here. Chris, could you explain us a bit what are those new connectors, what was the idea behind those, and the advantages of those?
Okay, yeah, great. Thanks, Guillaume. Yeah, so Senko developed the CS and SN connectors. They are both duplex connectors, and they both utilize LC ferrule technology. And what was the reason for these connectors being needed? So in the LC world, they were looking for increasing the density of, patch panels, transceivers, and the performance of an LC is great, but it can't get any smaller and sit in the same space. So the CS connector was developed using the same ferrule, but reducing the size and basically getting doubling the density into a transceiver. So if you looked at, this is a standard LC transceiver, right, with 2 fibers in it. And then if you went to the CS transceiver, so now it allows you to get 4 fibers or 2 connectors, 2 duplex connectors into that same footprint into a transceiver. So you're basically doubling the density in a transceiver, on a switch, on a patch panel, numerous different things. And then the SN was a similar thing. So that was more of an MPO-based requirement where you have 8 fibers into an MPO, a transceiver. And the way that the architectures were moving, you have a lot of different breakouts and shuffles to be able to go from end to end. And now we've developed the SN connector also with LC ferrules, but getting 8 fibers into the same size footprint as an MPO transceiver. So we can get 4 separate channels into an MPO instead of one connector that has all 8 fibers into it. So that's really the crux of why the 2 different things are going. So both connectors are lots of different options, connector options, adapter options, and a full ecosystem for as Expo has testing capabilities, and then we have the ability to make the cables and harnesses with polishing and all sorts of things. Let me see if I saw my other notes. Yeah, so really it was like a two-lane dual LC going to an SN or an MPO, or an 8-lane dual LC going to dual CS or an MPO to SN. Those type of solutions for the transceiver based. Both the CS and SN are being standardized. So the CS is being standardized by the TIA, and it is close to being a standardized product. With that organization, it has been adopted by the QSFP, DD, OSFP, and COBO as well for the multi-source agreements. And CSN is being standardized by the IEC for a worldwide standardization. And those are both in the process. Some typical breakouts like I was showing you with the transceivers, right? So here you would have the transceiver, a 2x100G to 2 LC 100G transceivers. This would be a typical application where you could see these connectors used. And then if you want to look at, how truly much smaller it is. So if I'm looking at this row here, this is 128 channels on a 1U, this particular application. And then you look below it, it's 2U space, still with 128 channels, but taking up 2U's worth of space using an LC. So really you're seeing how much space savings you can have. And then depending on the application, is it a co-location, right? They got to rent space. So that all matters. So that's kind of like the synopsis of the CS and SN.
Great, thanks for the overview, Chris. So we see the density is really the key advantage, I believe, of those connectors, the footprint being so small.
Yep.
Okay, so really, really interesting. So now let me switch to my other camera. It's a camera that's going to show my table, and I'm going to show you the inspection piece, how to look at those connectors with a fiber inspection microscope. We'll have also to enable this nice background. Disable it. Okay. All right. So here we have those connectors. So this is the CS1. So as Chris mentioned, within this we have two ferrules. So it's a duplex connector. And the size of the ferrule here are the 1.25 millimeter, similar to what we find in LC type of connectors. So now I'm going to use my EXFO fiber inspection scope. So this is EXFO's FIP435B. So there are two things I'm going to show. First, how to inspect a patch cord, and then how to inspect through a bulkhead. So of course, the patch panel, exactly like the one Chris was showing. So inspecting through this patch panel, I would be through a bulkhead. So first, let's look at how to inspect this connector here. Well, you might already have a tip that is the universal 1.25 millimeter tip. So this tip can be used for LC, but it can also be used to inspect the ferrule of those CS connector. So I would simply put this tip on my fiber inspection scope. I screw it in there. So this fiber inspection scope is a unit that is wireless. So you can connect it to your phone. And on your phone, that's where you have your application, your screen, where you see the connector view. So I would simply insert this connector here. And you see it fits properly. Again, it's one ferrule at a time. It's going to do the focus, take a capture. It gives me the status, the pass-fail status in green here. I see this connector is good. Those were fairly new connectors. Here I can see the image I have of this pass-fail result. So simply using a regular universal 1.25 millimeter adapter, I can look at the patch cord side. To look into a bulkhead, we have a new connector that was designed specifically to support the CS. So that is the connector. So here it's going to look at one ferrule at a time. We always want to inspect one ferrule at a time to assess the quality, make sure it's good, clean it if need be, before connecting it. So on this tip, I see an arrow here at the bottom that tells me which of the two ports it's going to inspect. So this is the one here, the one where I have a lens. Again, to install this tip on my fiber inspection scope, I would simply screw it in place here. Okay. So this is something, you can change in the field, fairly easy to do. You just screw this wheel here. Then I'm going to take the bulkhead. So again, this is mainly used if I want to test through a patch panel, or instead of switching tips to go from the patch cord side to the panel side, I can use a bulkhead to check my jumpers as well. So once I'm in a bulkhead like this, I would insert it. So here I would inspect the top connector. This is what my arrow here is telling me. So I just get it in there. So it fits properly in this. I would just start the inspection, and then automatically the image is captured, everything is focused. I see on this one here, I have a small residue. So what do I do if I have such a residue? I have a fail here. You have different cleaning tools that are available. Here I'm showing Senko's connector one-click cleaner for, it works for LC, but specifically also for CS. So this is a cleaner that is similarly to the inspection tip is going to clean one ferrule at a time. Okay, one of those two will be clean at a time. So here it's the top one. So again, I inspected my top one, it's bad. I'm going to clean it. Clean the top one. 1, 2. Then let's see if this debris was loose, if it was cleaned by this pen. So I start the inspection again. You can see here on the image that the connector looks good. There's no more debris there. My status is green here, so it is a pass. So this is how I was able to clean this connector. So this is probably the easiest way to clean a connector. I personally think that those one-click pens are easy to use, easy to carry around. You can replace the cassette if you want to refill them. But sometimes it's possible that the debris is kind of embedded on the surface. It's kind of stuck there. So then there are other cleaning methods that are available. You have what we call the hybrid cleaning method. So this one is dry. There's no solvent use. It's just, dry material. The specialized tissue in here is gonna clean the surface. So if I had something stuck, I could use a regular cleaning wipe. And if I want to do the hybrid method, so then I would take a bit of solvent. So typically what I would do, I would take this fiber wash cleaning pan that includes isopropyl alcohol, a solvent here. So I can put some on my cleaning tissue here. So this is a specialized cleaning tissue. It's not a regular tissue. So I would take the ferrule. I would do one pass on this wet material, and then I would make sure it is properly dried. So I do 2 passes on the dry surface. So now I will plug it back in, and then we're gonna see if what we get. So let me take another capture here. So in this case, it's properly clean, nothing there, nothing. So perfect surface, green status, so my connector is good. So those are kind of the ways to inspect such a connector. So again, I have the specialized CS tip that is available to look into the bulkhead that can be used in a patch panel with a bulkhead to inspect patch cords. Or just to inspect patch cord, I can reuse my universal 1.25 millimeter tip that is specially for LC, but in this case, since it's the same ferrule, it works also for CS. And then to clean, I can use my one-click, or as I showed, the combination of those two for the wet cleaning. So this is the demonstration that I wanted to do. I did this demonstration using Exfo's FIP-435B, which is our wireless fiber inspection scope. Exfo, I'll also take this occasion to say that we launched a new fiber inspection scope, which is the FIP-500, that has a nice color screen embedded in it, that has a quick connect mechanism to change tips, that supports multi-fiber, supports single fiber. So this is a multi-fiber setup. I can change the optical adapter like this to support single fiber. So currently we support CS inspection on the FIP-435B. And next month, towards the end in June, I should say, mid-June, we'll support it also on the FIP-500, which is the latest generation of fiber inspection tool we have at Expo. So this is going to be a complete solution for you when working with your CS connectors. So this is what I wanted to show regarding this. So with this being said, I'll now pass it over to my colleague Annabelle, who's going to talk about protocol testing.
Thank you, Guillaume. So let me start sharing my screen. Thank you. So I just want to go super quickly through some slides to show you or explain you what is the setup that I have here. And well, as we like said on the other sessions, like these type of connectors like CS are following up the development for 400 gig. So the idea of these type of interconnections in the context of protocol or in the context of data center, they are good to help the customers to easily migrate from 100 gig interconnections to 400 gig. And the different pieces of these kind of connections that are called breakout cables are three. The fiber, that we have different type of connections and fibers. The new connectors like SN, CS, and of course LC and MPO. And the transceivers, each type of transceiver is also very particular, either on the 400 gig side or on the 100 gig side. So to give you a perspective of how that is, this is one example of the type of breakouts that are out there in the market. On the 400 gig side, you have an MPO connector or a SN connector that then is splitting the signal into 4 different 100 gig signals, like we are seeing it here. On the connector side, in this example, I have an MPO, but in this case, you could have an SN connector. And on the other side, we have an LC connector. On the 400 gig transceiver, the type of transceiver that we see that are capable of doing this could be DR4, DR4+, or in the case of SN, FR4 or LR4. This is the type of the new transceivers that are coming out that have four wavelengths from 100 gig. And on the 100 gig side, here we're talking about specific transceivers too that are called single lambda that can be FR1 or LR1. So with this combination, some of the carriers that we know that are moving to the edge or having more cord installations in their facilities, they are using this type of cable for connections to slowly migrate to 400 gig, because the advantage is you could start with just one link and then slowly start connecting the other ones. That's the advantage. You don't really need to start filling all the bandwidth from the 400 gig transceiver. You could start with one and then migrate to a second one and so on. The way to test this type of connections, there are 3 ways. The first one is when they are deployed on the field. Basically, they are already connected to the switches or routers to interconnect either top of the rack switches in the aggregation layer or aggregation layer to the distribution layer. So the idea is in each side, you can have a tester that can generate either on one side the 400 gig pipe, and it will be received on the 100 gig side on another test set, like you're seeing here. Or when you have the cable connected to just the high-speed side, let's say the 400 gig side, and the other fibers like the LC connector, you can loop them. And in that way, you are validating the fiber and the high-speed transceiver. And the third case is when you have a test equipment on both sides, but you don't have any switcher or a router. You are really connecting the cable directly to the test set. In this case, you will be validating the 3 elements: the transceiver on the high-speed side, the fiber, and the transceivers on the 100 gig side. This is the one that we suggest before deployment, because in that way you will make sure each one is working correctly. So with that, I'm going to go to the demo. This is the setup that I have. In this side, I have a 400 gig unit. This is the one that is really generating the 400 gig pipe. And on each side, I have 100 gig transceivers being received via tested. Okay. So basically, what I'm doing is generating a bit error rate test directly from a 400 gig transceiver, is split it into 4 100 gig bird tests. And the advantage of this feature, or the flexibility that it brings, is each one of the links is a separate entity. So as you can see, we can see the status of the link on each of the session or each of the links. You can even decide if you want to validate the 4 at the same time, or if you want to validate each one, or if you want to validate 2, 3. We have this enable button where it allows you to select which of these links you want to validate. In this case, I'm running the 4. When you check the information of each link, we provide you here the power on each of the links. And we provide you here also the information of the whole transceiver that is associated to this 400 gig pipe. In this case, here I have a DR4. On the protocol side, this is a layer 2 test, but we can see anyway, in case of need, the MAC addresses on each of the links. And the important part is we can also configure bit error rate parameters per each link. So this really gives you the flexibility to validate each of the different links that are part of this breakout cable. In this case, for example, I went ahead and configured different characteristics for you to see its different types of links. Each link is almost independent. So link 1, I configure EMIX. So if we come here to the statistics on the other side of the link, on the 100 gig side, we have different packet sizes. So this can emulate almost like a real traffic. And in this case, I'm going to show you, this is the 100 gig side. And in the 100 gig side, we also provide you the power consumption on that type of transceiver. And here is where we can see that this is a very specific transceiver. This is a DR1. And this one has just one lane. And as you can see here, you can see the power of that transceiver. And we can see also that you have all the specifications for the bit error rate for that test. Okay. So I can show you another one. Let's go to link 2. This one I configured it with just a fixed packet size with 64. So that's why here we are seeing the statistics on just the 64 bucket. And if I go to the third one, in this one, I configure a packet size from 2000. So if we come here to the GUI, we can see that most of the traffic is being sent to the 1518 bucket because the packet size is 2000. And if we go to the last link, if you see, you can really navigate easily between the links with these controls. And in the last configuration, what I did is selecting PRBS 23. And if I go to my configuration here, so as you can see, each link can have different configurations. So this is really flexible on that sense. And you could really validate how the traffic goes per link. Another very interesting test that we suggest to do before deploying this type of cables is injecting errors. So I'm going to come to the results and I'm going to show you. Another element very important is that each element has, or each link has its own configuration, but it also has its own alarm and errors panel. So to really validate that the line is clean or there are no problems on the link, the ideal scenario is to inject errors to make sure that from your high-speed side to the 100 gig side, you can see the errors and you can confirm that when you send it, the other elements receives it. So on the 400 gig side, on the first link, I'm going to inject one error. And I see it right here, right? With this test, I can see that the connection is correct, that the fibers are correct, and the traffic is going without problems, and the alarms are being identified correctly, okay? And we can do exactly the same on each of the links, and we could, in that way, validate that the line is working correctly. So those are part of the elements that these features bring to the line. Let me show you. Let's go to the last link. We're going to see the alarms. So with that, we can see the alarms on all of them. And also, even if one of the links goes down, the global verdict is going to go down, but we're going to see the traffic is going to continue flowing of the other ones, because that's another important characteristic. The 4 links are not bind to the status. They can continue sending traffic even if one is down. So I'm going to turn off the first one. And we're going to see that we have an alarm that says there's no traffic, but the other tests are continue running. As you can see here, we still have traffic on the other. Just the one that I turned off. Just the one that I turned off, it stopped sending traffic. That's why I have a no traffic here. But in general, the others are continue going. And you can see here that we have an indication here that in the first connection, there's a problem with the pattern sync. So that right there gives you information of what's going on. And if we go to the results, we can see that this is the link that is showing the problem. So like this, you can see that this setup is very flexible. It can give you information of each link, and each link has its own characteristics for bit error rate, for packet size, everything. So that was basically what I wanted to show you. So I just wanted to let you know that we have a more in-depth material related to this type of breakouts in our webinar section. So if you want to go in depth to this type of subject, we already have a webinar that we did with our friend Chris from Senko that has even more details about these elements.
So thank you very much for joining.